First of all, you all have copies of the lectures. We will now start to introduce quantum chemical methods, and I want to start with a few famous quotes. And so let's go all the way back and quote two people who say something really important. So we will have a fairly technical course here, and we will do science in a way as it's being done in modern times, in a fairly utilitaristic way. And we should never forget that science in reality, of course, started by being curious about nature and by being curious about why things are the way they are. So no matter how technology or application driven you work, don't forget that we all began science at some point because we were wondering why things are the way they are, and we were curious about nature. So this is a first thing. And in terms of theoretical chemistry, there actually was an amazing amount of pessimism, and let's quote this gentleman. It's a philosopher, Isidore Marie-Auguste François-Xavier Comte, and he said a while ago, like, any attempt to use mathematical methods for the investigation of chemical questions must be considered as completely irrational and is strongly opposing the spirit of chemistry. If mathematics will ever occupy a prominent place in chemistry, an absurd idea that fortunately is completely unrealistic, this would lead to a rapid and irreversible decay of this scientific discipline. From today's perspective, it sounds a bit comical, I would say. And it also proves to you that nothing is absurd enough that not at least one philosopher in the history has claimed it. And actually, that's also a big difference and an important difference between philosophy and science. Now, of course, Comte was proven wrong. And just 50 years later, roughly, the great physicists of their time, Schrödinger, Heisenberg, and Dirac, they invented quantum mechanics. So roughly at the same time, Schrödinger and Heisenberg invented wave mechanics and matrix mechanics. And although we talk about the Schrödinger equation, most of the time what we actually do is much closer to what Heisenberg has done. So in reality, in the computer, we do matrix mechanics, not wave mechanics. Although there is, of course, a clean mathematical connection between both of them, and we're going to explore that at least a little bit. And then the connection between quantum mechanics and the theory of relativity, that was done by Dirac, and that goes very, very deep into the theory of like the cornerstones of physics. And you will hear a little bit about that if you attend the special interest group about relativity. Now, even there's a famous quote, and this famous quote is also due to Dirac, and I think one could well call it Dirac's legacy. So what Dirac said right after he found this equation, and he was a fairly young man now, so I guess he was well below 30, and he said, the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry, so all of chemistry, is completely known, and the difficulty lies only in the fact that application of these laws are too complex, lead to equations that are too complex to be solved. So Dirac said that conceptually we understand everything. The only problem is an engineering type problem. These equations are just too complicated. And to some extent, we are still working as theoretical chemists on Dirac's legacy, trying to solve these equations that he considered to be too complicated to be solved at the time. And less well known is that the quote goes on, and he said, hence it would be desirable to develop practical approximation schemes for the application of quantum mechanics, and this is what we do, and this is what you will exercise today and the next few days during this course. Now, we have started from boundless pessimism, and it went all the way to boundless optimism. And boundless optimism was already expressed by Enrico Clementi, who is a famous computational chemist. He's still around, and he sometimes even calls at my office in Bonn when he wants to speak to my predecessor. And he said in 1975, we can calculate everything. And of course, this is as unjustified as to claim that you can calculate nothing. So today, I think it is fair to say that we can calculate a lot, but we can certainly not calculate everything, and we likely never will be able to calculate everything. But nevertheless, mathematical models, quantum chemical methods are a very important aspect of modern chemical research, and the fact that you are here, although your special interest is not theoretical chemistry, already shows you and shows me and shows all of us how important it becomes to have some familiarity with the methods of quantum chemistry. So quantum chemistry is useful, and so what we hope to bring over is in which way it is useful and to educate you in how to use it. So why would you want to do quantum chemistry? And I guess some of you are here to do quantum chemistry in order to predict quantities that cannot be measured. So sometimes a species just doesn't live long enough to be observed, or the experiment to observe it would be way too complicated, or it would be way too expensive. So for example, if you want to synthesize an entire protein with sulfur-33, that's going to be really expensive because a milligram of sulfur-33 costs about 5,000 euros or so. And so if you want to have 10 grams of it, that's an expensive experiment, and I don't think your boss would like you to try to do that. So, and in these cases, you hope to fill in the blanks that where experiment doesn't provide you information quantum chemistry can. But this is perhaps not even the most important part. What is important to many of us and many of you is that you want to do quantum chemistry in order to interpret the outcome of experiments. So you sit in front of your data and you wonder, what the hell does it mean? And in this situation, you can turn to quantum chemistry and get help. You may not get a final answer, but you get a lot of help. And the typical situation are the really complicated NMR and EPR spectra that you get for complicated molecules. But of course, you ask your quantum chemistry to be more than that, more than just numbers. What you want is to obtain insight into trends of data. And so that is a totally different type of application of theory. Quantum chemistry in itself is a theory that applies to individual single molecules. And in that respect, every molecule is different. But of course, chemists are used to think in terms of series and small modifications. And so, of course, we all know that if you make a small modification, the properties of your molecule usually don't change in an irregular way. It changes in a regular way. And of course, organic chemists, for example, know so much about functional groups in molecules. And you want to understand that from a theoretical point of view, and you want to find a language to talk about these things. And this is not at all obvious that it's possible, but it is. And in order to find this language, you need to go away from the rigorous application of quantum mechanics into kind of pictorial quantum chemistry. And at that point, it becomes a kind of an art rather than a science. And of course, you want to predict the outcome of future experiments. For example, you want to design materials with certain properties. So what do you have to do to make your molecule magnetic? What do you do to make your molecule conducting? What do you make to make your molecule colored in a specific way? These are all questions that you can address in quantum chemistry if you use a virtual laboratory. So if you draw down molecules, do the calculations, calculate these properties, and then pick the best candidates for selecting the property that you want. And I think this is an increasingly important aspect of quantum chemistry because it saves a lot of time and a lot of money also. So it's a cheap way of designing materials and selecting the best candidates for the purpose. And there may be many other reasons that I haven't named, and some of you may have different motivation, and I hope most of you it's not to please your boss, but to do something useful with quantum chemistry. Yeah? Now, let's start. And so what are the interactions that we're talking about in quantum chemistry? And first of all, it's important to realize that these fundamental interactions are really, really simple. And it's reassuring to some extent that underneath, down at the bottom, things are simple. It's just the complexity arises from the many particles that make up atoms, and atoms that make up molecules, and molecules that make up assemblies, and so on and so forth. This is where the complexity arises. But deep down, it's simple, and it's just electrostatics. So you have negatively charged electrons and positively charged nuclei, and so the only thing you need there is Coulomb's law to tell you that like charges repel each other, and unlike charges attract each other, and the interaction goes as 1 over the distance between these two charges. So this is all there is. You have the electron-electron repulsion, the nuclear-nuclear repulsion, the electron-nuclear attraction. The only thing you have to add to that is the kinetic energy of the particles. So as you know, a particle moves with a certain velocity. It has an energy, and the energy is 1/2 times the mass times the velocity squared, or in other words, it's the momentum squared divided by 2 times the mass. And so this is all there is. And in principle, you can explain all of chemistry with it. Everything that you call like resonance or hybridization or aromaticity and all these complicated things that chemists talk about all day long, they're all contained just in the electrostatics plus the kinetic energy. So it's good to sit down and relax and be happy about the fact that deep down the interactions are simple. It's just many of these interactions add up to be complicated. So you can catch a glimpse of that if you think about a billiard table and you have these 20 billiard balls and you move them all at the same time and you want to calculate which ball is where at which point in time. And so this is a gross oversimplification of the many particle problem that you have in quantum mechanics and in particular in quantum chemistry. Now, of course, this is all entire classical, and now we have to move from classical to quantum mechanics. And in classical mechanics, of course, you know that the motion of the particles are described by Newton's equations. And if you solve Newton's equations, you will have the positions r and momenta p of all of the particles as functions of time. Yeah? And the solutions are r of t and p of t, and that is what in classical mechanics you call the trajectory of the particles. In quantum mechanics, of course, you know that the uncertainty principle forbids us to know the momenta and the positions both at the same time, but instead we are aiming at something more modest, which is the wave function of the system. And the wave function provides us with a probability of finding the particles at given points in space, at given points in time, and a more precise definition we will come back to later. In order to calculate that wave function, a special form of the equations of motions from Newton is required, and that is the so-called Hamiltonian formalism. And that turned out to be the most useful formulation of classical mechanics that maps over to quantum mechanics in a simple way. And the Hamiltonian of the system corresponds to its total energy. So we just have to write down the terms that make up the total energy. And so based on what I've said, it's fairly easy to write down these terms that make up the total energy. So we write the Hamiltonian as a function r. Small r means all of the positions of the electrons, and capital R means all of the positions of the nuclei. And so these are just the kinetic energy of the electrons, the kinetic energy of the nuclei, the electron-nuclear attraction, the electron-electron repulsion, and the nuclear-nuclear repulsion. And so it's really easy to do that by summing the kinetic energy of each particle. So that is a sum over I, and small I sums over electrons, pi squared divided by 2 times the mass of the electron, and the nuclear kinetic energy in the same way. And for the electrostatic, the Coulomb terms, we just have to sum over pairs of particles. So pairs of electrons that repel each other by 1 over the distance, pairs of nuclei that repel each other, and pairs of electrons and nuclei that attract each other. So that's basically all, and now we have to translate that to quantum mechanics, and that's really simple because the Coulomb terms stay as they are in classical mechanics, and the only thing you have to do is to replace the momentum by the quantum mechanical analog of the momentum, and this is the operator minus I, where I is the imaginary unit times the gradient operator. And in quantum chemistry, it is really customary to work with a special system of units because we don't want to carry all of these factors like 4 pi epsilon 0 or h bar or the elementary charge E0 or the mass of the electron around, so we all set them to 1. Yeah? And that is a great simplification of these equations, and that means in a quantum chemical calculation, numbers come out in that specific atomic unit system. And so when your program prints a number of you and it's an energy, it's typically in Hartree. And a Hartree is 27.21 electron volts. An electron volt is 8,000 wave numbers or 23 kilocalories per mole. So different people have different units that they like, but it's really important that you develop a feeling what's a large number and what's a small number in whatever unit system you want to have. Yeah? So typically chemists like to think in terms of kilocalories per mole, and so that means one Hartree, one atomic unit of energy, is 627 kilocalories per mole. So that's a very large number. And that already tells you what the curse of quantum chemistry is. So in order to do chemistry, we need to predict energies about to a kilocalorie per mole. That means we need to calculate the energy to about 3 significant digits at least. Yeah? So this is the curse of quantum chemistry. So there is one more step that we have to do in order to proceed from classical mechanics to quantum mechanics, and that I will do that in a brute force way this morning, and Dimitri Ganyushin will do it in a more precise way this afternoon, is to introduce the spin of the electron. So the electron just not only has 3 spatial variables, x, y, and z, that describes its position, but there is a 4th one, the spin variable. And there is a spin variable, and the spin of the electron is associated with a magnetic moment. And this magnetic moment is probed by EPR spectroscopy, and we will talk about that on Friday morning. Now, the only thing that is important is that you add to the 3 spatial variables 1 spin variable, and you collect that in a vector x. Yeah? So x is a 4-dimensional vector that contains 3 spatial degrees of freedom for each electron and 1 spin degree of freedom. Now, given all that, the Schrödinger equation that is the fundamental equation of non-relativistic quantum mechanics is the following, and it reads that the time derivative of the wave function, the many-particle wave function, as a function of x, so all electron coordinates, r, all nuclear coordinates, and time, equals the Hamiltonian operator that we have just written down times the wave function itself. And so this is a time-dependent Schrödinger equation, and so whenever your system is evolving, or your system is non-static, your system is in a non-stationary state, you have to deal with the time-dependent Schrödinger equation. We will do very, very little of that in this course, and so most of the time we are talking about molecules in stationary states. And for those, a simpler equation applies, and that is the time-independent Schrödinger equation here, and that tells you that the application of the Hamiltonian operator to the many-particle wave function equals the energy times the many-particle wave function. So the energy is a scalar quantity, and that means what this is an eigenvalue equation, and the solutions of the eigenvalue equations are first of all the many-particle wave functions, and second of all the total energy. And as every eigenvalue equation has many solutions, so has the many-particle Schrödinger equation. There is one more step that we need to do before we come to those formulations that start to be practical, and that is the Born-Oppenheimer approximation. So in the Born-Oppenheimer approximation, we neglect the kinetic energy of the nuclei, and that means we come to the illusion that the nuclei are at rest and are at specific positions. And so that means the Hamiltonian goes over from the Hamiltonian we just wrote down to the so-called Born-Oppenheimer Hamiltonian that is the basis of almost all quantum chemistry, and that just contains the kinetic energy of the electrons and then the 3 electrostatic terms. And the justification for that is that the nuclei are so much heavier than the electrons. Already for the hydrogen atom, it's almost a factor of 10,000. And so the electrons move a lot faster than the nuclei, and the Born-Oppenheimer approximation amounts to assuming that the electrons are immediately following each nuclear movement. So this is the Born-Oppenheimer approximation, and it's absolutely fundamental for chemistry, because how would you be able to talk about the structure of a molecule if you couldn't pin down the nuclei and tell us where they are? Yeah? So the Born-Oppenheimer approximation itself is what lets us talk about chemistry in the framework of quantum mechanics. It's a very important step. Mathematically, it's actually ill-defined, which is not very reassuring, but the practical consequences are not very large. So that is consequence number one, the concept of a chemical structure, and secondly, the concept of a potential energy surface. That means what we do and what you will do in the course is to solve the Born-Oppenheimer equation as a function of nuclear position. So you have the nuclei in a given configuration. Say you have a diatomic molecule and you have a certain distance, and then you start to move one of these nuclei and you recalculate the energy, and then you move it again and you recalculate the energy, and you move it again and you recalculate the energy. And what you get will be a smooth curve of the energy as a function of distance, and this is so-called potential energy surface. I will come back to that. And the consequence number two is that the Schrödinger equation separates into two equations. One for the electrons, for any given arrangement of the nuclei, and that gives you the potential energy surface that I've written down now here as a function of the nuclear coordinates r. And secondly, one Schrödinger equation for the nuclei, that is this equation here, that gives you the nuclear wave function, and the nuclear wave function is what you probe by vibrational spectroscopy. And the total wave function is then the product of the electronic wave function and the nuclear wave function. But we are almost exclusively concerned in this course with the electronic wave function. Now, is the Born-Oppenheimer approximation good? Yes, it is. So it describes more than 99% of all chemistry correctly and with almost arbitrary accuracy. So deviations from the Born-Oppenheimer approximation are typically extremely small. It's on the order of a few wave numbers, so a few micro Hartrees, so 10 to the minus 6 atomic units, or like a very small fraction of a kcal in the total energy. That is okay. So, but what is not contained yet in the Born-Oppenheimer Hamiltonian, there are no terms so far that describe the interactions of nuclei and electrons with external electric and magnetic fields, and we will have to add these terms when we talk about spectroscopy, of course, because when we do an EPR experiment or an NMR experiment or an absorption spectroscopic experiment, what we do add is external electric and magnetic fields. So, and these will have to be supplemented to the Born-Oppenheimer Hamiltonian. It misses many of the small terms that are associated with electron spins and nuclear spins, and this is something that will come up in the relativity lecture this afternoon and will also come up in the EPR lecture on Friday morning. The Born-Oppenheimer Hamiltonian obviously does assume a point-type nucleus, and this is not really true because nuclei also have a shape. Just from the perspective of an electron, the nucleus looks incredibly much like a point charge. And there are small deviations from that, and those of you who are accustomed with EPR and NMR spectroscopy know that there is something like the quadrupole interaction, and the quadrupole interaction arises because the nuclei are not actually point charges. The Born-Oppenheimer approximation just breaks down in a situation where the separation of nuclei and electronic movements is no longer possible, and that happens when the nuclei move really fast. And that happens in Jahn-Teller systems, for example, that are used to you. For those who do inorganic chemistry, you know about that. And in this situation, you have to go beyond the Born-Oppenheimer approximation. And of course, there are a number of relativistic terms that do become important when heavy elements are involved. So if you think about the core electrons that are close to the nucleus, and if you go down the periodic table to, for example, Mercury, the inner shell electrons start to move close to the speed of light, and that means when something moves close to the speed of light, its mass changes, and then you have to apply the rules of relativity. These effects are small for most of chemistry, but they're not negligible, and some of them are really important for all of spectroscopy. And for example, you explain nothing in EPR spectroscopy if you neglect relativity, because there is nothing you can explain without spin-orbit coupling, which is a genuine relativistic term. Yeah? So these are the limitations of the Born-Oppenheimer approximation. Now let's talk about the many-particle wave function. And what is the many-particle wave function? And its meaning is defined by the Born interpretation. And the Born interpretation tells us that the square of this wave function, so psi star times psi, defines the probability of finding the system in this configuration of variables if it's in state psi. Yeah? So if the system is described by psi, and given a certain nuclear configuration R, then psi star gives the probability for finding electron 1 at position R1 with spin sigma 1, electron 2 at R2 with spin sigma 2, and so on and so forth up to the nth electron. So this is all we are ever allowed to know in terms of quantum mechanics of n-particle systems. There is nothing more we could possibly know. And this is already much more information than we actually need. But I come back to that in a second. So the second absolutely super fundamental property of that wave function is the Pauli principle. And the Pauli principle, you know from your freshman chemistry, states that no two electrons can have the same quantum number. But this is not what the actual Pauli principle. The actual Pauli principle tells you if you have the many-particle wave function psi that has coordinates in x1 all the way to xn, and you exchange two sets of particle coordinates, the many-particle wave function has to change its sign. So it's got to be anti-symmetric with respect to particle interchanges. And that defines the properties of electrons being so-called fermions. This seems really odd. And it is odd. But there is nothing else that we can do except to accept the fact that nature has been built this way. Experimentally, there is no doubt that the Pauli principle applies, and there is no known case of the violation of the Pauli principle. So it's one of the absolutely fundamental laws of nature that the many-particle wave function has this property, whether we like it or not. Then, of course, you ask yourself the question, like, damn, I mean, that looks like a complicated wave function. It has like all these n electron coordinates and these nuclear coordinates, and how do I get a picture in my head? How do I understand that wave function? The answer is you don't. Nobody does. So the n-particle wave function is an object that is way, way, way too complicated to be understood in pictorial terms. Yeah, so nobody can intuitively picture a function of 4n variables. So that means the insight into how it behaves has to come from somewhere else. And very importantly, so for those of you who have seen that psi and have thought about psi orbital, that's wrong. So there is no orbital here yet whatsoever. So if you think that orbitals are fundamental objects of molecular theory, that's not right. So you could do all of molecular quantum mechanics without ever touching the word orbital. That's not the way it's being done, but that's the way the truth is. So if we could solve the Schrödinger equation for the many-particle wave function, we would never have to talk about orbitals. So please think about that. Orbitals will turn out to be building blocks for such a many-particle wave function, but there is nothing fundamental in them. So what is the total energy that we get out of the Schrödinger equation if we can solve it? So the total energy, E, is the energy that is required to separate the molecule into non-interacting protons and electrons. So actually nuclei and electrons. So take the n electrons and bring them, all of them, into infinite distance of each other so that they don't interact anymore. And take all the nuclei and bring them into infinite distance so they don't interact among each other and they don't interact with the electrons anymore. That is the total energy. So the difference between that is defined as energy 0. Is the total energy observable? In principle, yes. So if you like explode your molecule and measure like into electrons and nuclei, and measure how much energy it takes, in principle, yes. But in practice, of course, you never do that experiment. So from a practical point of view, the total energy itself is not an observable. But instead, what we do in chemistry, we measure differences in total energy. And these differences are relevant. And that means there is a great opportunity for cancellation of errors. And in fact, we never really calculate an accurate total energy. But what we calculate is accurate energy differences. That's the only thing we can do. And how large is the total energy? That's a very large number. for a transition metal complex, typically say 10 to 100,000 electron volts. But if we want to do chemistry, as I said, we need to have it accurate to about 0.1 electron volt. So that you see how substantial the challenge is to come up with accurate total energies. As I said, the Schrödinger equation does not only have one solution, so H psi equals E psi, does not only have one solution psi and one solution E, it has many solutions. Like any differential equation, it has even an infinite number of solutions, and they differ by energy. Yeah? And so there is one energy that is the lowest of all, and that is called the ground state energy, and that we call E0. And that, of course, is the most important energy because it defines how the molecules are when we just let them sit. So in the test tube, your molecule is typically in energy state psi 0 with energy E0. And all of the other energies, EI, for I larger or 0, are the excited states of the molecule. And that means for each excited state energy, there is a different many-particle wave function psi I. If two or several of these energies are identical, we say that the state is n-fold degenerate. And we will talk a lot about degenerate states. For example, in EPR spectroscopy, in the absence of a magnetic field, there are 2s+1 states of the same energy. Yeah? And importantly, eigenfunctions that belong to the same degenerate eigenvalue are only determined up to an arbitrary unitary transformation. For example, if you have a doubly degenerate state, and they are described by wave functions psi1 and psi2, you can take the combination 1 over square root 2 psi1 plus minus psi2, and you end up with the same description of the system. So these eigenfunctions are only determined up to an arbitrary unitary transformation. And these eigenfunctions can be classified, and we will come back to that tomorrow in much more detail, at least according to 3 criteria. So these eigenfunctions have a definite value of the total spin S. Yeah? And that 2s plus 1 is called the multiplicity, and that is the spin degeneracy of a given state with a total spin S. Yeah? And as we talk about open shell systems, this is the important quantity, the total spin S. Together with the total spin S, I think you have learned in your freshman chemistry that there belongs a second quantum number, and that second quantum number is called M, and that's called the spin projection or the magnetic quantum number that we will discuss later. And EPR spectroscopy is about inducing transitions between states of the same S and different M. And as molecules have symmetry, the eigenfunctions of the Born-Oppenheimer Hamiltonian also have symmetry, and that means we can classify these states with respect to their overall spatial symmetry, and that is described by so-called irreducible representation, which we will talk very little about, but I assume that most of you have heard an introductory course about group theory and you are familiar with that concept. And that means we can write these eigenfunctions as psi I is then the given eigenvalue, and psi I has a given total spin S, a given magnetic quantum number M, and a given symmetry quantum number, if you want, so gamma. And that is how we characterize these states. Now, chemistry and potential energy surfaces. Now we look at the potential energy surface of the ground state, and that defines our chemistry, because we start out somewhere here at the local minimum of the potential energy surface that we call reactants. And then we displace, for example, by thermal fluctuations or by some other kind of action, the system, and its energy increases, and it goes to a saddle point of the energy, and that we call transition state. And the energy difference between the transition state and the ground state and the local minimum here for the reactants, that's of course the activation energy. And that's closely related to the rate constant of a reaction. And then the system may relax back to a different state that might well be the global minimum, and that we would call the reaction products. And so this is a potential energy surface, and much of quantum chemistry is concerned with calculating these potential energy surface. And the second major application of quantum mechanics, of course, is spectroscopy. And so what we're going to do here is to leave the system in a given nuclear configuration, but induce transitions between different states of the system. And these transitions occur under the action of a photon, of course. And we will talk on Friday a lot about spectroscopy, of course. But the probability that a given photon induces such a transition, that is given by a famous rule, and that is called Fermi's golden rule. And that tells you that the probability for that transition, and that means ultimately the intensity of the spectral peak that you observe, is proportional to the square of the matrix element, and this is this one, so the initial state wave function and the final state wave function under the action of the perturbing Hamiltonian of the light wave. So that's basically an electric field Hamiltonian that enters here, H1, and under this action, the system changes from psi initial to psi final, and the probability for doing so is given by the square of that matrix element. So these are, that is spectroscopy. And spectroscopy can come in very many flavors and variations. And I've just written down the most important one for the inorganic chemist, and it starts with core level spectroscopy with gamma rays on the order of 14,000 electron volts, and that would be a Mössbauer experiment. So a Mössbauer experiment involves a 14,000 electron volt transition between nuclear states of the system, and you measure a very small energy difference here. And so this energy is too high to typically excite the core electrons even. Then between 2,000 and 8,000 electron volts, you excite core electrons, 1s electrons, into the valence shell and into the continuum, and that is core level spectroscopy. You do that at a synchrotron, and that would be X-ray absorption spectroscopy and extended X-ray absorption fine structure, EXAFS. Now, the optical spectroscopy that you use in pretty much every chemistry lab, that happens at much, much, much lower energy, 1 to 4 electron volts. That's a visible part of the electromagnetic spectrum. And what you do there is you excite valence electrons. Yeah? So those electrons that are in the valence shell, and that gives rise to various flavors of optical spectroscopy like absorption spectroscopy, magnetic circular dichroism, or circular dichroism, or many other kinds of optical spectroscopy. Now we go down in energy like by another 1 to 2 orders of magnitude, and then you can no longer excite electrons, but you only be able to excite nuclear transitions, and that gives rise to vibrational spectroscopy as you measure it with infrared spectroscopy or Raman spectroscopy. And another 2 to 3 orders of magnitude less in energy, that's microwaves, 10 to the minus 4 to 10 to the minus 5 electron volts. And there you cannot even excite nuclear vibrational transitions, but you excite electron spin transitions, and that's electron paramagnetic resonance. And another 2 orders of magnitude in energy less, then you can even no longer excite an electron spin transition, but you only can excite nuclear spin transitions, and that gives rise to nuclear magnetic resonance and Endor spectroscopy. So you see, there is a tremendous range of like 11 orders of magnitude in photon energy that is being covered by spectroscopy, and it's really important to have that in the back of your mind when you talk about spectroscopy, like what is the energy scale that you're actually talking about. And remember, 1 atomic unit, 27 electron volt, 1 electron volt, 8,000 wave numbers, or 23 kilocalorie per mole, and 1 wave number, about 30,000 megahertz. Now, how do we solve the many-particle Born-Oppenheimer equation? And the answer is not at all. It's impossible to solve this equation exactly and to write down a wave function as soon as we have more than 1 electron. So for 1 electron, there are a few toy problems that you can solve, and one of them, of course, is the hydrogen atom. But already for the helium atom with 2 electrons, we can no longer solve the Born-Oppenheimer problem. That's really frustrating. And that means we need approximation methods. And what approximation methods exist? So this is the equation that we want to solve, or that we want to approximately solve, and that is the Born-Oppenheimer Schrödinger equation. Yeah? And so the simplest approximation method, that is Hartree-Fock theory that we're going to talk about in a minute. And Hartree-Fock theory will turn out to be not accurate enough, and it can be followed up by so-called post-Hartree-Fock treatments like configuration interaction, many-body perturbation theory, and coupled cluster theory. And Andreas Hansen will talk about that to those of you who are attending his special interest group lectures. And this is approaching the exact solution of the Born-Oppenheimer problem, slowly but surely. And so today we are able to generate very nearly exact solutions for small molecules. So up to about 10 to the minus 4 Hartree, we can really solve the Born-Oppenheimer Schrödinger equation. But these are methods that are much too expensive to use it on an everyday scale. Now, the Hartree-Fock equations can be simplified and then supplemented by empirical parameters, and that gives rise to the field of semi-empirical quantum chemistry. And then if you throw away every quantum aspect of it, you arrive finally at force fields. And force fields you can apply to very large molecules with tens of thousands of atoms. And Christoph Rieplinger will talk about in his special interest group lecture of how to apply molecular mechanics in conjunction with quantum mechanics to large molecules. And now, of course, you are here because I know that some of you refer to this as not a theoretical chemistry school, but a DFT school. And so in contemporary chemistry, pretty much the words theoretical chemistry and density functional theory, DFT, are used interchangeably, and that's not right. But it's just due to the fact that there is that theory called density functional theory, and density functional theory has about the same computational cost as Hartree-Fock theory, but is almost always better than it. Yeah? So it comes in terms of accuracy somewhere between Hartree-Fock and post-Hartree-Fock methods, but it's a much, much more practical approach to molecular electronic structure. But that shouldn't distract from the fact that the only way to systematically approach the solution of the Born-Oppenheimer equation is to travel down this road. Yeah? Now, how does it come about? And the most important step here is the variational principle. So just imagine you have in your hands or your pockets, you take out a certain wave function psi trial. Yeah? So a wave function that you think might well be a good approximation to the state that you want to calculate as a function of x and r. And you may introduce some free parameters p that you want to change to make the wave function approach the solution of the Born-Oppenheimer Schrödinger equation. Then there is a very powerful device which is called the Ritz functional, and that is the expectation value of the Born-Oppenheimer Hamiltonian over the trial wave function divided by its norm gives you an energy, of course, and that is an energy is a functional of the wave function psi trial. And of course, if you have the exact wave function, E of psi is the exact energy, of course. For any other wave function, you can easily show that E of psi is larger than the exact energy. And that is great, because that means now you can take the Ritz functional and your free parameters and vary them to find a minimum of this E of psi. And you know for sure from this condition that as you lower the energy, you are getting a better approximation to the true psi. Yeah? So that means you can massage a psi to become better, and become a better approximation to the true wave function. And a very extreme way to explore that is the Hartree-Fock method. So the Hartree-Fock method starts from a very unrealistic system. It starts from a system where the electrons are supposed to not interact anymore. So you have all of the electrons at infinite distance and they don't interact anymore. Then the Born-Oppenheimer problem would be very, very simple. Because then you would simply have to solve, instead of one n-electron problem, you would have to solve n one-electron problems. And as I told you, a one-electron problem we can't solve. And what would be the many-particle wave function that would come out of such a system that is separable, that consists of independent particles? It would be a simple product, a product of one-particle wave functions. And that product that we call a Hartree product, but that's not permissible in terms of quantum mechanics because we got to satisfy the Pauli principle. It must be anti-symmetric in the particle coordinates. And the easiest way to satisfy that is to write that product wave function as a so-called Slater determinant. So now we have introduced one particle wave functions, small psi1 to psi n, and we have the n electron coordinates x1 to xn, and we put them into such a determinant, and as you know from mathematics, such a determinant has a property of changing its sign when you interchange its rows or its columns. And this Slater determinant would then be a correct solution for non-interacting electrons. And the one-particle wave functions that we put in here would be solutions of the one-particle Schrödinger equations of the independent particles. And these are the things we call orbitals. Yeah? So these one-particle wave functions we call orbitals. But how do we get that now? And the idea of Hartree-Fock theory is to take this wave function that we know is not realistic, but it's the only starting point that we have, because that's the only type of system we can solve, and put that into the variational principle. And then we have to vary something to make it better. And what we can vary are the orbitals themselves, so the one-particle wave function. So we change each and every one of these one-particle wave functions under the constraint that they stay orthogonal and arrive at the best possible single determinant. That is Hartree-Fock theory. And in order to do that, we are really poor people in quantum chemistry, because we can't even really solve exactly our one-particle problems, but instead we have to expand these orbitals again. Yeah? Because the orbitals themselves, their shapes are so complicated that we cannot really exactly calculate them, but we can only approximately calculate them. And we calculate them by expanding each orbital as a linear combination of so-called basis functions phi mu. And if our basis set, so the collection of all phi mu, becomes mathematically complete, this is an equality sign. And in any other case, it's an approximate equality. That is very sad. And so we have to introduce, instead of unknown psi's, we introduce unknown coefficients c mu I. So for each molecular orbital I, we have a linear combination over all functions of the basis set to describe it. Now, of course, the choice of basis set is a very important step in every quantum chemical study, and Frank Venmos in the next lecture will tell you more about the intricacies of basis sets and all these things. Yeah? But that means now the variational principle boils down to just determine these coefficients c mu I, because the basis functions we keep fixed. And so we will not go through the mathematics, but the mathematical analysis shows you that this leads to the so-called Hartree-Fock-Rotan equations, and that the molecular orbital coefficients must satisfy a set of nonlinear equations, and they read f times psi I equals epsilon I times psi I. Yeah, and so all of this is finite, and we write that in matrix form. And so we have a so-called Fock matrix. So instead of the many electron Born-Oppenheimer operator H, we now have a Fock operator F. And the Fock operator F, that depends on its own eigenfunctions. I will show you in a way soon. And so all of this is basically a matrix eigenvalue problem that with a modern computer you can solve very efficiently, and you will do that, of course, today. Now, what is the Fock operator? The Fock operator is basically the mean energy of an electron that occupies an orbital psi I in the presence of all other electrons. Yeah? So the orbital energy epsilon I is the expectation value of the Fock operator, and that is the one electron energy of the orbital psi I. And that is the expectation value over the kinetic energy of the electron and the electron nuclear attraction. And then there is an average electron-electron interaction. And this is given by this integral, two-electron integral here with these two bars. And it comes in two cases. And so the first case, that is the interaction of an electron that occupies psi I with an electron that occupies another orbital psi j. So electron 1 sits in psi I, electron 2 sits in psi j, and so psi I squared is then the probability distribution for psi I, and psi j squared is the probability distribution of psi j. And so we simply now have here the electrostatic interaction between a charge cloud psi I squared and a charge cloud psi j squared. So this is entirely classical physics. It's just the interaction between two charge clouds. So smeared out charge distributions. And of course, the Coulomb integral is always positive because the distance is positive and the square of the orbitals is also positive. And the second part of this double bar integral is so-called exchange integral. And the exchange integral is a bit weird because it's the interaction of an interference density, if you want so, between psi I and psi j with itself. And that is something that is entirely quantum mechanical. So there is no classical analog of the exchange integral, and some people even speak about the exchange interaction, but that's not correct, because the only reason the exchange integral is there is because the wave functions got to be antisymmetric. So the reason for this being there is the Pauli principle. And the interaction is entirely electrostatic. There is no such thing as an exchange interaction in nature. So please consider that. Those of you in particular who have a background in magnetism, they are so used to talk about an exchange interaction. There is no exchange interaction. There is no Hamiltonian describing an exchange interaction. Yeah? So all of this is just a consequence of electron-electron repulsion in conjunction with the Pauli principle. That's all there is. There is no exchange interaction in nature. And you don't see it from this equation, but you can prove that also the exchange integral is always positive. But since it enters with a negative sign into the Hartree-Fock equations, the exchange energy lowers the total energy. So pictorially speaking, what have we done in Hartree-Fock theory? Instead of trying to solve the n-particle problem, we have replaced it by an effective one-particle problem. And so our reference electrons, so the one that we like sit on, yeah, is having a kinetic energy, it's having an electron nuclear attraction, and it swims in the sea, in the field, in the average field of all other electrons. Yeah? So that's why Hartree-Fock theory is also called a mean field model in the sense of the physicists. Yeah? And so the average electron-electron interaction here, that is also called the Hartree-Fock sea. Now, how do we solve the Hartree-Fock equations? And you will do that a lot, and so that's why I'll be brief. The Fock operator obviously depends on its own eigenfunctions because the Fock operator contained terms in psi j, so the solutions of the Hartree-Fock equations themselves. And that means they are very nonlinear equations, and you have to start an iterative process. And you do that by guessing some starting orbitals, and you just have to guess. I mean, there is no other way. You have to guess, but most of the time the programs are doing that for you. It would be really hard if you would have to do it yourself. But the programs come up with some guess. Then you calculate the Fock operator with the present set of orbitals. You diagonalize it to obtain new orbitals. You calculate the total energy. You check if the old orbitals and the new orbitals, or the old energy and the new energy match. They are the same. And if they are the same, you say you have reached a self-consistent field. Yeah? So that means you are satisfying the Hartree-Fock equations and the electrons move in a self-consistent field. And as long as this is not the case, you go back and calculate a new Fock operator with the new orbitals and so on and so forth. And if it happens to converge, and that can sometimes be a real big pain, and especially if you do transition metal calculations, you say, hooray, and you're converged. And then you print the results and do additional calculation, calculate properties, and so on and so forth. But first of all, you have to go through the pain of solving the Hartree-Fock equations. Convergence may be slow. Convergence may not occur at all. Convergence may occur to a higher energy solution that you didn't want. Convergence may occur to an unphysical solution. You have no guarantee whatsoever. You need to check, you need to be careful, and you need to be patient. That is Hartree-Fock theory. How good is Hartree-Fock theory? Now consider the neon atom has 10 electrons, and the exact Hartree-Fock energy we know is minus 128.547 Hartrees, and the exact experimental energy is, by summing the 10 ionization potentials of the neon atom, is minus 129.056. So you would say, wow, this is really cool. That is, Hartree-Fock recovers 99.6 of the exact energy, and if you subtract a little bit of relativity, you would even think it recovers 99.8% of the total energy. And that, of course, is spectacular given how simple the idea of Hartree-Fock theory was. But the bad news is the conversion factor really works against us. As I said, 1 Hartree, 27 electron volts, 627 kcal. That means that small error in the Hartree-Fock energy of 0.2% just amounts to the very large error of 320 kcal per mole. But in chemistry, you just need to have 1 kcal per mole. And that means Hartree-Fock theory is just 2 orders of magnitude off. Yeah, and you have that error of a few hundred kcal for each atom. So if you have a 10 atom molecule, then of course it's 3,000 kilocalories. And if you have a 100 atom, then it's a 30,000 kcal error. And that's really too large. And to calculate these energies exactly really is very hard. But we want relative energies, and there it's still hard to come to 1 kcal. So what is really missing from Hartree-Fock theory? The exact energy, of course, is the mean field energy that we do calculate in Hartree-Fock. And what's missing from that is what is beyond the average field of the other electrons. So an instantaneous electron-electron interaction process. And there are 2 types of electron-electron interactions. So electron-electron interactions between electrons of the same spin, and that is relatively easy. So if the electrons have the same spin, they don't repel each other that strongly because of the exchange interaction, and that is what we call Fermi correlation. Or the electrons have opposite spin, and then they repel each other very strongly, and that is what we call Coulomb correlation. And the Coulomb correlation is extremely difficult to calculate. And so most of the difficulty to calculate accurate molecular energies comes from the difficulties to calculate the electron repulsion between electrons of opposite spin. So here's a little picture of how you can picture that instantaneous electron-electron interaction. So as we see, the electrons swim in their Hartree-Fock sea. But the Hartree-Fock sea is something that is really boiling. So it's boiling like lava. And so you see when 2 electrons approach each other, 1 or 2 or 3 of them like jump out of their occupied Hartree-Fock orbitals into unoccupied orbitals. And so what you have to calculate is the probability of these electrons bumping into each other and jumping into higher energy orbitals. And that can occur as pairs of electrons, triples of electrons, quadruples of electrons at a time. And the modern quantum chemistry allows you to do that, and allows you to do that in a very accurate way. And there we use advanced methods of many-body physics that we're not being able to cover here in that course, but it is possible, based on this picture, to calculate very accurate correlation energies, and that means very accurate total energies. Now there is the interpretation, of course, of the Hartree-Fock equations. And the primary result of Hartree-Fock calculations, once it is converged, is of course the total energy, and that is the sum of the nuclear-nuclear repulsion, that is a constant for a given nuclear arrangement, the 1 electron energy, and the average 2 electron energy. And of course you have the approximate many electron wave function, which is just that Slater determinant that we write in this way. But there are these secondary auxiliary quantities that also come out of the Hartree-Fock equations. And these are the orbital energies, epsilon I, and the orbitals themselves. And the orbital energies roughly have the interpretation that it's the energy that it takes to remove the electron from the molecule. So that's an ionization energy. And this is called Koopman theory. And the orbitals themselves, of course, you are very used to interpret these orbitals all day long. And it starts from from organic chemistry, where you see all kinds of orbitals in your lectures, and inorganic chemistry, where you see all kinds of orbitals in your lectures. But rigorously speaking, there is no fundamental importance, despite the fact of HOMO, LUMO, and other arguments. In practice, of course, the orbitals is what describe the electronic structure of the molecules in terms of bonding orbitals, anti-bonding orbitals, or lone pairs, and we will come back to that, of course, also in that course. It's a subject of endless fights and debates, but remember, deep down, orbitals themselves don't have a physical meaning. Now, let's talk about the electron density. So the electron density is, of course, also something that comes out of these calculations, and it's simply the sum over all occupied Hartree-Fock orbitals squared. As you see, that is a weakly structured function of space that is always positive and that is fairly insensitive to bonding. So if you just take the electron densities of the neutral atoms and superimpose them, you basically see no difference to the actual molecular density. And this is actually the way that crystallographers solve their structures. So they make use of the fact that forming a bond is a minor perturbation on the total electron density. It really is very, very small. Yeah, and the electron density is then the sum of the densities of the spin-up and spin-down orbitals, of course, or if you write it in a different way, as a sum of the spin-up and spin-down densities. Now, of course, in chemistry, we want to think of polar groups and partial charges and all that, and so we want to break down the total electron density into manageable parts that belong to individual atoms. And as you see, of course, from the actual density, there is no unique way to do that. And so every scheme that tries to come up with these partial charges makes something that is not well defined. Actually, there are very many ways to distribute that electron density among atoms, and they are all called population analysis. The easiest is due to Mulliken. Refined schemes are, and that is very popular, so natural population analysis, NPA, that is also implemented in most programs, or the atoms and molecules approach from Bader. But partial charges are not physical observables. Yeah? So it's nothing well-defined quantum mechanically that is a partial charge. And that means if you're interested in that, just stick to one of those schemes and look at the trends. Yeah? So there is no better partial charge or no worse partial charge. The opposite of the electron density is the spin density. That's a strongly structured function of space. It's either positive or negative, and it's highly sensitive to bonding. And in Hartree-Fock theory, that is very similar to the total electron density, but instead of summing the contribution of the spin-up and spin-down electrons, you take the difference between them. So it's a difference between the density of the spin-up and the density of the spin-down electrons. And that is, of course, the thing that you measure in EPR spectroscopy. And as you can see, as you are very sensitive to bonding, you have a very clean and very powerful connection between EPR spectroscopy and chemical bonding, unlike in crystallography, where the total electron density is not sensitive. Now I think we have to rush a little bit because we're running it relatively late, but I think I have to tell you a little bit about density functional theory because it's so basic to what we're going to do. Now there is a powerful theory awarded with the Nobel Prize 1998, and that tells you that in order to calculate the total energy, what you do need is just the electron density, and that is absolutely surprising. Because of the electron density is a one electron object. Yeah? It just lives from one set of electron coordinates. But the electron-electron repulsion that you need to calculate the total energy is, of course, a two-electron object because it depends on the distribution function of the probability of finding a given pair of electrons at a given distance. So it seems absurd that you should be able to calculate from the electron density that knows nothing about electron pairs the total energy. But in principle, it's possible, and that is the so-called Hohenberg-Kohn theorems, and this is for what Walter Kohn got the Nobel Prize together with John Popel for making it practical. Now let's look at the fundamental idea of density functional theory. So here is the electron density of the CO molecule, and you see it has a strong peak at the position of the carbon nucleus, and it has a strong peak that is a little bit higher at the position of the oxygen nucleus. And you see there is a cusp here at these nuclear positions. And of course, you know, if you integrate over all space, you get the total number of electrons, because that's the nature of the electron density. That means, and from this equation here, the height of the cusp is related to the nuclear charge. That means, from the electron density, you can A, figure out where are the nuclei. From the height of the cusp, you can figure out what is the nuclear charge. And from the integral over the electron density, you can figure out how many electrons you have. And that means, since the only term in the Born-Oppenheimer Hamiltonian that depends on the actual shape of the molecule is the electron-nuclear attraction, that means you can reconstruct the entire Born-Oppenheimer Hamiltonian from the knowledge of the density alone. And if you can reconstruct the Born-Oppenheimer Hamiltonian, and you could solve it, you would have the exact wave function and the exact energy. So let me iterate. If you know the electron density, you can deduce the number of electrons and the electron-nuclear potential. From that, you can deduce the Born-Oppenheimer Hamiltonian, and we have written it down. And if you could solve the Schrödinger equation, you would have the exact solution. Now you say, wait a moment, this is cheating. I mean, we knew the Hamiltonian before, and we couldn't solve the Schrödinger equation. Yeah, so that's it. We knew the Hamiltonian before and couldn't solve it. And just the Hohenberg-Kohn theorem just reassures you that you can get at this stage where you don't know what to do with one step more. That's it. That's all there is. Yeah? And it was worth the Nobel Prize. So you see, sometimes it doesn't take much. So actually, no, I mean, it's more powerful. The rigorous mathematical analysis shows you that it should be somehow possible to bypass this thing that we can't do and arrive there without having to solve the many-particle Schrödinger equation. And the big dream is to be able to do that. But we don't know how. And I doubt we ever will. Yeah? So, but the existence of that universal functional E of rho is guaranteed by the first Hohenberg-Kohn theorem. And the second Hohenberg-Kohn theorem, that is again a variational principle, and it tells you that given a test density rho prime, and you would have the exact universal functional E of rho, you would end up with an energy that is too high, and that would mean you can massage your density to better energies and so on and so forth. But the critical point is that, of course, we don't know that recipe E of rho to calculate the exact energy from the density. Well, I think I skipped that. That is like the mathematical apparatus. But the important point, like for making it practical, is the so-called Kohn-Sham construction. Now, we have talked about Hartree-Fock theory. And there we introduced the independent particle model in order to motivate the Hartree-Fock equations. Now, with Kohn-Sham theory, in density functional theory, you do something really similar, but you invent another reference system, a fictitious system of non-interacting electrons. And as we know from Hartree-Fock theory, its electron density would be the square of the occupied orbitals summed over. That's the exact electron density. Now, the important step in Kohn-Sham theory is you construct a Kohn-Sham single determinant for that fictitious reference system that has one constraint. The Kohn-Sham electron density matches the exact electron density of the interacting system. Yeah, so, and by this you make a connection between the effective one particle part and the many electron physics. That is an ingenious construction, and it leads you to equations that very, very much resemble the Hartree-Fock equations. So basically what people did when density functional theory came up, they took their old Hartree-Fock programs, threw away the exchange part, and replaced it by an effective potential, the so-called Kohn-Sham potential. And the Kohn-Sham potential, that's a functional derivative of that universal functional and so on and so forth. But this is now the magic potential, and if you would solve these Hartree-Fock type equations that you can do for large molecules, you would end up with the exact solution if you only would know the exact functional, but you don't. Now there are, just to give you a realistic view of where we stand with these functionals. Now, realistically speaking, we can today calculate at ridiculous computational cost pretty much exact potentials. And you have shown them here in red an exchange potential and a correlation potential for the argon atom. So this is how they look. Yeah? And we know the exchange potential's got to be 1 over r in the large limit, in the large distance limit. For the correlation potential, we don't know much. And here in blue, you see one of the popular density functionals that we use today, the so-called PBE functional. And you see, yeah, I mean, for the exchange potential, it's, yeah, well, yeah, it's not so bad. But you see it falls off much too quickly. And the fact that it falls off much too quickly means the Kohn-Sham energies of present-day functionals are way too high. They're 5, 6 electron volts too high, and that's why they don't approximate ionization potentials well. But the important part is look at the correlation potential. This would be the exact correlation potential, and the PBE correlation potential doesn't match it at all. So even minus the PBE potential would be a better approximation to the exact one than the PBE potential. So you should keep that in mind. We have these potentials. There's a huge variety of density functionals out, and they give extremely useful results, but they don't get it for the right reason. Whenever you do Kohn-Sham density functional theory, you rely on a huge cancellation of errors. So, and I think in order to not keep you too long for the rest of your coffee break, we stop here and and just sum up what we have done in this lecture. So we have talked about that chemistry is described by the many-particle Schrödinger equation. The Born-Oppenheimer approximation is a cornerstone of molecular theory and almost always is accurate enough. The many-particle Schrödinger equation cannot be solved exactly. A useful first step towards its solution is Hartree-Fock theory that recovers about 99.8% of the exact energy, but the remaining error is still way too large to do chemistry with it. With post-Hartree-Fock methods, you can approach the desired chemical accuracy of a kcal per mole, but that's computationally still too expensive for widespread application. This is true today, and I firmly believe this is no longer true in 5 years. So stay tuned. There is big hope to apply these post-Hartree-Fock calculations to chemistry in a big way in the foreseeable future. And this is also some of the research that we do in Bonn. For the time being, it's density functional theory that offers an efficient but very pragmatic approach toward usefully accurate chemical results that with present-day models, DFT models, and Frank Venmus will talk more about that, are semi-empirical in nature, and they all involve the cancellation of large errors. So thank you very much for staying tuned. Sorry for taking some of your coffee break time, and we reassemble then probably in 20 minutes here. Thank you.